In this tutorial, I am going to discuss about the common source amplifier with the diode-connected load. Before going to discuss about the amplifier basic, let's see something about the diode-connected device. Let me draw the NMOS. And this is gate, and this is drain, and this is source, right? So what happened if we connect the gate and the drain? So when we connect the gate and the drain, what happened that Vg equals to Vd, right? And this is VDD, this is VSS. Okay. So to maintain in saturation region, we know that for NMOS that should we follow this criteria, right? So as we see that Vg equals to Vd, so what happened? We can write this expression, right? So that means this MOSFET in its saturation region, right?
Right.
This will always in saturation region. And the next thing is that what is the expression for this current which is flows from the drain to source? Okay. So this current is basically half V and Cx W by L Vgs minus Vts whole square, right? Or we can also write it yeah. So what will be the ID versus VDS? So in y-axis this is ID, and x-axis we can say that BDS or VGS both are the same. So the curve look like that. After the threshold voltage, it will look like, sorry, this one, right? And from this curve we see that in a diode which is in forward bias look like same response, right? So that's why it's called in diode connected device. Okay, so what will be the small signal equivalent model for this specific circuit? Let's see. So and this is gate, right? And this voltage is VGS. You can say VGS or VDS, both the same. So this is the gate and the drain. And the gate and the drain are shorted. The next thing to write a dependent current source. And this is GM and VGS, right? And the next thing, have to add a internal resistance, right? RTS. And this terminal is Vout. Oh, sorry, this is not Vout. This is VDS, right? Okay. So now let's solve this circuit to find the output impedance or output resistance. Let okay. And now let's put test current. Oops. Ix in here. Solve this expression circuit for Ix. Ix equals to, yeah, one current is GM times VGS, right? And another current can write that this one. So which is VDS divided by RDS1. So we can write that the VGS equals to VDS, right? Because the VG equals to VD. And this one. So we can common VDS. So okay. On the other hand, if we simplify that one upon RDS, right? Sorry, these things not Ix by VDS. This thing is VDS by Ix, right? So anything V by I, which is nothing but R out. So we can further simplify it, and finally we get that one upon GM 1, or simply GM parallel RDS. So if we neglect that the lambda effect equals to 0, we can simply write that R out equals to 1 upon GM, because that the RDS1, which is much greater than the 1 upon GM, right? The current always flows in low impedance path. That's why R out equals to 1 upon GM. So we get the output impedance of this diode-connected device. And now we have to simulate it in Cadence and see the curve will look like this or not. So this is the Cadence Virtuoso window library manager. So let's create a new library. So let's get a MOSFET. So then MOS. Let's put the gate and the drain is short. Right. And now we need the DC voltage. Let's put it to 0 for VSS and for 1.8 for PDC. Now some label. And the body is also connected to the source. Perfect. Then let's go to the ADL. DC. It will go to 0 to 1.8. Okay. Going to plot this current, right? Yeah. You can see that after the threshold voltage, what is the threshold voltage? Let me make this plot better to view. Tap in. Yeah. And then make it more thick. And the axis we can not necessary. Okay. So the threshold voltage looks like around this one, right? Around 400, around 500 millivolt, right? To approximately 500 millivolt. We can also check it from the DC operating point. So, yeah, it is around, it's say around 542, right? So we can approximate to this is the threshold voltage, and after the threshold voltage it will go as a rise up, and this curve will not look like perfectly this one, right, due to the channel length modulation. And if we let's let me make it variable. Now I'm going to from 500 nano to 5 micro. I'm going to plot 10 step. Sorry, I'm going to here. Let's see what is the effect if we vary the length. Yeah, if we increase the length, the channel length modulation effect is reduces, and this fulfill our expectation, right? Because we are assuming that the curve will look like this one. This one not perfectly, because this is a open-handed handwriting. Okay, this is the practical demo what we learn in theory.